Okay, this is lecture 14 on invariant maximality derivations by Harvey Friedman, please.
Okay, so we're in chapter three. The entire updated reversal chapter four, which we spent all those lectures on, is now just one link, not these excerpts, and updated some in the downloadable manuscripts page. I won't be working on this anymore, chapter four, until I get feedback and or maybe just before I submit things for publication. So chapter four is kind of, so to speak, done, whatever that word means. Um, Now, lecture notes for lecture 13 last week is where we ended at 4.2, is on my downloadable lecture notes page, and then the manuscript version that has the proofs and everything is on my downloadable manuscripts page. I think that goes to 3.4. All right, so let's just take stock at where we are here. The book is called Invariant Maximality. The current title is Invariant Maximality, Finite Constructions in Games. Um, and I'm thinking of September 1. I'm trying to wrap everything up. Uh, and uh, I'm thinking that uh, by middle July, I think by middle July, chapter three should be uh, done. Uh, by middle of July, chapter three. Then there's uh, some cleanup work, some perfection of this is needed, uh, but probably we'll go to this. Uh, this won't be as big as these other chapters, but this is for explicitly pi zero one, and that's important. And then this also there's some important things. Uh, I already know that games helps in in refining the finite constructions and actually makes for some simplifications. So I know that this chapter is worthwhile. All right, but I don't think that these are going to be the same length as these other things. These are the heavy chapters. All right, so the table of contents for this chapter three that we are going through um, is uh, we skipped this. I haven't really written this, um, or I haven't written a polished form of it at least. So last time we did this and this, and we got into this to here. Um, and now we want to start here. Start here. Okay. And this is the way this goes. Usability refers to the invariance function. In other words, a function is usable if, roughly speaking, a function is usable um, when uh, when you can use it in the uh, in the statements we're interested in. So I use the word usable. One usable means one dimensional, and that's a very basic thing that's not difficult to deal with. Ah, yes. So I did some serious work on this in the last few days. Uh, all the statements involved so far are not explicitly pi zero one, but they're implicitly pi zero one. And I develop a theory of this. This is actually quite interesting. Some interesting things come up here today. and then and this important fact that basically all of the statements that we're really interested in are implicitly pi 0, 1. The explicitly pi 0, 1 forms come only in this chapter. That's where the explicitly pi 0, 1 forms come, and some of here. Okay. All right, and then the finite case is actually quite substantial. The finite case is quite substantial, but fully understood. Finite case is fully understood. Um, we won't get that today, but next week, this is the this we're going to discuss this in detail and probably do this, just the introduction. And then the following week after that is the real heavy meat, the main event of chapter 3, where I prove all these statements in these theories. And finally, I use SRP or con SRP. This is the key one. Yeah. And then there's some more stuff because there's some more things that I can handle. And there's a general theory, the attempt at a general theory of what's usable. Obviously, that's that's going to be a long road for research to really understand what's usable and what isn't. These are very special cases, but they already challenge what set theory you have. All right, so let's start. So this is a section called invariant maximality. All right, so we already talked about the main lead statement. Okay, the lead template of the whole of the invariant maximality, recall, is every order constraint has a F invariant maximal solution, and that has only one free variable, namely F. F is the function. It's a partial function from -1, 1 to 1, -1, 1. By the way, we leave the Q off. It's understood that every number in this book at this point, every number in this book is irrational. The only real numbers that are not rationals are in chapter 2, which is the background material in core math. Okay, so this is the lead template. Every order constraint on the S contained in -1, 1 to the K has a K invariant maximal solution. And if you remember, an order constraint is just a condition of the form S to the R is contained in E, where E has dimension K times R. Okay. And we're looking for maximal solutions. All right. So now we have these other forms, these other templates. Every order invariant set contains an F invariant maximal square. Every order invariant subset has an F invariant maximal root. Every finite subset has an F invariant maximal Ord square. Every finite subset has an F invariant maximal emulator. This is the one that's most suitable that I use for gifted high school. And when I did it for gifted high school, of course, K = 2. And the finite set was cardinality 1 trivial, 2 tricky, 3 hard. I was able to do it for cardinality 3 in dimension 2. This is exactly what I did for them. And that's all in RCA naught. That can be done by hand. Cardinality 4 is a much bigger deal. It might be doable by hand. It's not clear. All right, let's not get into that right now, but that's really quite interesting, I think. All right. Um, every ordered invariant relation has an F invariant maximal free set. Every ordered invariant graph has an F invariant maximal clique. Every ordered invariant graph has an F invariant maximal independent set. All right. The convention is that all free variables are interpreted universally unless otherwise indicated. And here in the above 8 statements, F is not interpreted universally, is treated as the parameter, of course. That's why I call these a template. OC max F is the lead template of invariant maximality, and the remaining 7 above are, I call the secondary templates of invariant maximality. So the lead template, once again, is every order constraint has an F invariant maximal solution. Now, we did a reversal on this guy where F was that favorite function, 0 minus 1 0 semicolon 0 over k dot 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 1 over 0 over n dot 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 1 over n, and we even let k equals n, and this is what we reversed. Okay. Now we also discussed the templates above resulting from fixing the dimension k. And we do that by writing colon k, colon k, colon k. 1, 2, 3, 4, 5, 6, 7, 8 statements, colon k, where k is fixed and not universally quantified. Okay, so we have these templates for each dimension. All right, now equivalences and implications. The first thing we want to do is clear the air that you can always reduce dimension. In other words, if the dimension goes up, you get a stronger statement. Yeah, it will be strictly stronger, but that's stronger. In other words, it implies it. So the statement for k plus 1 implies a statement for k, and this is organized as follows. We have a lemma that says that if I have a constraint, this is an order constraint. If I have an order constraint of dimension k, and remember the order constraints can have any dimensionality R associated with them, but order constraints of dimension k, then I can always find one of dimension k plus 1 such that the solutions to the one of dimension k are just the so S is a solution in S is a solution of dimension k. Yeah, this is, what do I got here? S to the R. Yeah, this is all screwed up. Sorry about this. Yeah. And by the way, this may not be the same R. This might not be the same R. I should just do this. Yeah. Fix this up a little bit. Okay. And this is straight, this is easy to prove. In other words, we just added dimension. Now, and then the lemma is for every order constraint on the S, there exists an order constraint on one higher dimension such that S is a solution to the first if and only if S cross minus 1, 1 is a solution to the second. Yeah, that's what I really want to say. but when you wind up proving this, you wind up proving this more technical, this more a little bit more specialized. I mean, it's essentially the same thing. Yeah, just restated. And then every order constraint on the S dimension K, there's an order constraint on the K plus one, such that S is a maximal solution. So these were not necessarily maximal to the first if and only if this is a maximal solution to the second. And then S is F invariant if and only if S cross minus 1, 1 is F invariant. You always have that. Okay, and then we finally proved the following. The lead and secondary templates with colon K plus 1 implies the lead and secondary templates with colon K. So this is just that you can reduce dimension. Also, the lead template with colon K implies all of the secondary templates with colon K. You see, because all of those other things are, all of those other variants are in fact examples of order constraints. In one case with a maximal square case, the maximal cube case or maximal square case. In one case, it's you only have that the maximal uh, the maximal objects are just the maximal constraints that they're just examples of order constraints that for maximality. They're examples of maximal order constraints. Yeah. So that's all in the detailed manuscript. Okay. All right. So that's enough of general nonsense connected with the thing. They're very easy things, namely that dimension reduction and dimension reduction even for any of the variants. You have dimension reduction. And the lead template covers everybody else. Okay. All right. Now we get into something more substantial. Uh, yeah, I didn't know this until fairly recently, uh, that um, almost all of the secondary, all of those secondary templates um, imply outright the lead template, except one of them. There's one of them that's a little weaker, but six of the seven um, uh, give you the full thing, the full thing, no matter what F is. I mean, we're not claiming that this is true dimension-wise. That's not the case. Well, I think I need a late section in the chapter about counterexamples in some way, but in fact, I'm not sure that I can do counterexamples easily. Yeah, that might be beyond the scope of what I know how to do because well, no, I think I can do a certain amount of that. Yes, certain amount of counterexamples. But anyways, we're not claiming something like this for every K. All right, so a bit of a tricky lemma that even with maximal roots, if you push the dimension up, you can force the maximal uh, root to be of the form S to the R. Yeah, so this is a tricky technical lemma, and we use this in order to show that OI max root of F already implies the full thing, order constraint max F. Okay, something I only knew recently. Now, um, We also want to get a result for emulators, but I'll say in order to do that, we have to use a modification of, we first use a modification of max root called max root prog, where we assume that we have order invariant progressive E. Order invariant progressive E has an F invariant maximal root. Okay, and then we show that the emulator form implies the max root prog form. We'd like to get that the max emulator form gives you the full max root form, because the max root form gives me the lead template, but we just get this. And then I'm able to actually show that you can go from the prod to the full OI max root F, which is nice. But I do need, for technical reasons, I do need that F has a fixed point, which is slightly annoying, but not serious, because we really only care about the Fs. All the Fs we're really interested in have fixed points. Um, so if F has a fixed point, then even the emulator one is equivalent to the max root one, which is equivalent to the full one, the lead template. There, that one. So everything is cool. We also can handle the maximal squares. The squares in E are not the same as the roots, as the squares of roots. Yeah, no, that's correct. Maximal squares are the same as the squares of the maximal roots. That's right. Um, and also we get that S is F invariant if and only if S squared is F invariant. These are trivial. So finally, we get the following big equivalence. All of our variants are all equivalent except the emulator one. The emulator one is a little special. If F is a fixed point, then the emulator one also is equivalent. So we basically have equivalence of all these variants. But if we fix the dimension K, things are a little bit trickier. Uh, if we fix the dimension K, then the full one, the lead template, which is not listed here, by the way, it's discussed only here. The full one seems to be stronger, although I'm not sure that actually I actually know a lot about that. There may be an issue of what I know, but it certainly doesn't follow by the techniques that I'm using here. So we get equivalence of all of the variants are these so-called secondary templates. We get the equivalence dimension-wise. In other words, all those equivalence proofs uh, preserve dimension, except for one of them, the emulator form. And the emulator form not only is a fixed point used, but you also have to go up one dimension in the proof that I have. You have to go up one dimension. So there's a number of open question, delicate, detailed open questions surrounding this. But in general, things are pretty well organized. My variants are in general pretty equivalent. Yeah. Okay. I also need for later purposes, I need some general global stuff. Two of them, two things like that. Is it uh, yeah, three of them, three things. Yeah. So if F and G are isomorphic, then uh, then you get an F invariant solution, no matter what the order equivalence is. You get if F and G are order isomorphic, then for the present purposes of invariant maximality, F and G are equivalent. That's all this is really saying. And that's, of course, totally unsurprising because you notice that invariant maximality is completely order invariant uh, in the sense of where you have to preserve the endpoints. The endpoints count. So that's why the endpoints are obviously in here, right? Okay. And another thing is that we want to make certain transformations. So minus E is the obvious thing. E is a set of vectors, right? So minus E is just a set of minus of the vectors. Now, if I have any function f, partial function, there's a function called minus of f, and that's where you deal with both the arguments and values. So minus f of p is is equal to where defined to minus of f of minus p. And given an order constraint, there's always um, the minus of the order constraint. So here we have an order condition on the S, uh, then minus alpha has an F invariant solution if and only if alpha has a minus F invariant solution. So this talks about what happens to our invariant maximality when we take minus of an order constraint. Well, this induces a mapping uh, uh, on the invariance notion, F, namely minus of F is what you want. Okay. Now, if F happens to be 1, 1, and by the way, if F isn't 1, 1, it's going to be highly unusable. So basically, everybody is going to be the only important Fs are 1, 1. In fact, the only important Fs are strictly increasing. We will see that later today. Talk about that. Uh, then S is F invariant if and only if S is F inverse invariant. So invariance, F invariance is the same as F inverse invariance. This is a kind of a triviality. Okay. These come up later when we actually get into the guts of this chapter, where we're actually showing uh, usability of basic functions. We don't have to redo work. We can take the inverse, for example. All right, so now we're going to talk about usability in general. And we haven't so far not even defined this, although intuitively you can imagine what this is. So F is usable if and only if you can use it. F is usable if and only if you can use it for the lead template, for the lead statement. All right, that obviously is a good definition. All right, now this definition is pretty stable in certain ways. It's the same as saying that all secondary templates for F hold. Okay, you don't have to use this is the lead template. All the secondary templates, so some secondary template holds other than the emulation one. That's equivalent. F is usable, this here. And if F is a fixed point, we can include emulation in 2. This is just a restatement in different language of what we've already discussed. Okay, now the next notion is fully K usable. Here, K is fixed. It means that the lead statement, the lead template holds in dimension K. F is K usable if and only if all, we just say K is usable, we don't put the word fully. K is usable if and only if all secondary templates hold for fixed K. All the secondary templates. See, the secondary templates are restricted or more down to earth in a way. The okay, so all right, so okay, now this is usability. So far, we've only talked about full usability, full K usability, and usability. It remains to talk about K usability. And that's the weakest notion of all, which is just the secondary templates hold for fixed K. So all secondary templates hold. Some secondary template holds other than these, and F is K usable. These are all the same. It's just that this emulation one has to be treated with more care. That's all. Just a little bit more care. Not a lot. All right. We're getting this screwed up here. Okay. I think I lost the place where I was at. Yeah. Okay. So we're here. Now, there are two necessary conditions. Um, the first one is highly non-technical and overriding importance. A function is strictly increasing. This is a partial function, if and only if when P is less than Q are in the domain, F of P is less than F of Q. F is strictly dominating if and only if F of P is bigger than P whenever P is in the domain. And strictly regressive if F of P is less than P for any P in the domain. Now, I don't think that I use strictly dominating and strictly regressive. I'm not sure I used that until much later in the chapter. So perhaps this should be defined later. But we certainly use this strictly increasing. All right, now if F is too usable, then F is strictly increasing. And I could have given a proof today of that, but I'm not going to. I mean, basically, uh, this is a simple exercise. If F is too usable, then F is strictly increasing. One usable won't work. You really need to look at pairs. And if you're going to deal with two usability, it's frequently simplest to work with the maximal root thing, that every ordered variant set in twice the dimension has an invariant root. Uh, and then this is pretty straightforward. Now there's a more technical, not too much more technical, second thing. I said two necessary conditions. And this is very much used, this other one is very much used when we get to the work on next week on finite usability of finite functions. All right, so let F be too usable. Then you can't, then F cannot be, you can't be pulling down from 1 at the same time raising from -1. You can't be pulling down from -1 at the same time be raising uh from -1. You can't be pulling down from 1 at the same time raising from -1. Now we know we can't be raising all the way up here from -1. That would violate strictly increasing. But I'm saying you can't go like this. You can't go like this. And you can't go, also you can't go like this. You can't go like this, and you can't go like this. As long as I'm talking about the endpoints. Okay, and that's much trickier. That's actually somewhat tricky to do that. But this is an important fact that we use next week. All right, now one usability, because I always talk about two usability here. One usability um, is completely determinable, is not a is a relatively easy matter to understand one usability. And RCA naught is enough. Um, so a function affects P if and only if there exists f of P equals Q, uh, or f of Q equals P, where P is not Q. In other words, f of P is either f of P is defined, either f moves P, maybe I should say, either f moves P or f inverse moves P. Another way of saying it, I think. Yeah. Okay. This is going to be important when I finally tell you what one usability is equivalent to. Okay. For the proof of what I'm going to tell you, I have to enumerate the ordered variant subsets of -1, 1 squared. And they're very simple. Here are the ordered variant subsets of -1, 1 squared. Just these sets, the only ordered invariant ones. Now, F is one usable if and only if some number is not affected by F. F is one usable if and only if there's some P that's not affected by F. Simple idea. All right. This also works for emulators. Um, if For emulators, F is one usable if and only if one usability is the same as just having it for emulators. You can adapt that. Now for full one usability, and that means that we're working with we don't need this here, where everything's rationals. Uh, for the full one usability, we're using the lead template. So we're talking about all order constraints. So that's a stronger notion than one usability, because one usability is just for these um, secondary templates. So the order constraints on, so we need a characterization of the order constraints in one dimension. An order constraint is equivalent to a disjunction of statements that mention the cardinality of the set S be constrained, you can possibly say that it's bigger than a number, bigger than something, or the maximal instances are just are either the whole space or the sets of some particular cardinality. Uh, yeah, you have to prove that you're not going to get anything uh, other than that. Okay, uh, so S is F invariant if and only if, yeah. So now we need a necessary and sufficient condition for being F invariant, where F is our usual kind of function. Uh, and S is a one-dimensional set. If S is a one-dimensional set, we can flat out say what it means to be F invariant. It means F of S union F inverse of S is contained in S. I mean, nothing that simple is going to work when S is higher dimensional, of course. So S is fully one usable if and only if for every I there exists an I element subset such that FA union F inverse A is contained in A. So that's the condition. That's a necessary and sufficient condition for full one usability. Okay, I didn't want to actually put the proof in here. It's a mistake. All right, now I want to talk about implicitly pi01. We're gonna prove that basically invariant maximality is an implicitly pi01 subject, right? Well, now we make it explicitly pi01 in chapter 5, but on the face of it, it's implicitly pi01, and we only need Gödel's completeness theorem to see this. So sometimes I say implicitly pi01 over WKL naught via 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 Gödel's completeness theorem. Okay. Now we have the well-known system WKL naught of reverse math. I have an appendix listing all the main systems. Now WKL is an extension of WKL naught, which we need in order for this theory that I'm about to talk to you about work smoothly. So WKL is WKL naught together with a full induction scheme, IND, in the language of second order arithmetic. And we define a pi01 sentence as usual. It's in the language of piano arithmetic with less than. It begins with zero or more universal quantifiers, followed by a formula with only bounded quantifiers. By bounded, I mean using this. All right. Phi is implicitly pi01 over WKL naught, or also WKL. And for simplicity, there's a more general theory where this is an arbitrary system, but this is what comes up in invariant maximality, and I just want to talk about these two. Okay, if and only if there exists a pi01 set in psi, such that WKL naught or WKL prove phi if and only if psi. That's what it means to be implicitly pi01, respectively. WKL naught, WKL naught, or WKL. Now, obviously, the one for WKL is going to be a little bit stronger. Not much, but somewhat stronger, right? Okay, So there's an important intuitively recognized property that implicitly pi01 sentences have. They have what I call falsifiability. Falsifiability is an important foundational concept in its own right. Phi is falsifiable over WKL not or WKL. And you can do this more generally. If and only if the following is provable in WKL not or WKL. If I'm false, then I'm refutable. If not phi, then WKL not proves not phi. So if I'm false, I can be proved to be false. Trivially, implicitly pi01 over WKL implies implicitly pi01 over WKL naught, certainly. And falsifiability over WKL implies falsifiability over WKL naught. That's clear. All right. If phi is implicitly pi01 over WKL naught, then phi is falsifiable over WKL naught. Now that's pretty clear because if you're pi01, asserting you're false is existential, and if you're false, you're provably false. So this is a very well-known kind of thing. And of course, it works just as well if you're in WKL. Does it make any difference, really? All right. But now I'm able to actually, oh, I'm sorry. This is not what I'm saying. I'm saying this is the easy direction. The hard direction is if you're falsifiable, then you're implicitly pi01. So in the case of WKL, not in the case of WKL, not in the case of WKL, I have an exact equivalence. Falsifiability and implicitly pi01 are the same. These are actually the same. This is interesting. So I summarize all the results because some of them are not quite right. You can't do this one here with WKL naught on both sides. All right. So if phi is implicitly pi01 over WKL, if and only if phi is falsifiable over WKL, as I said, and if phi is implicitly pi01 over WKL naught, then phi is falsifiable over WKL naught. But we don't have the reverse. Yeah, I think I can give a counterexample to that. We don't have the reverse, but we almost do. So basically, the lesson is that falsifiability and implicit pi01ness are basically the same thing. That's the idea. Now, in science, important hypotheses are normally falsifiable. That's why you run experiments and you get confirmation when you don't falsify them. But the idea that you could falsify them is very important, that the experiments could come out wrong. It's therefore somewhat persuasive to focus on statements in mathematics that are falsifiable in the sense I use here. Okay. Now, the last thing I want to do today uh, is show that invariant maximality is an implicitly pi01 subject with a later chapter that's explicitly pi01. All right. And the core idea is that the core notion is the core notion inside invariant maximality. The core notion is in fact pi01. In fact, demonstrably pi01 in WKL naught. Namely, asking whether there is an S which is maximal such that S to the R is contained in E and S is F invariant. This is actually just saying you're asking for a constraint, you're given an order constraint, and you're asking whether there's an F maximal solution. Just the heart of invariant maximality. I'm saying that as a function of the order constraint E and the invariance F, this is a pi zero one statement. But what do I mean? I mean, with E is presented as code with a code, and F is presented as a code. Then, in terms of the codes, this is uh, pi zero one. See, I'm only claiming that invariant maximality is a pi zero one subject um, when E and F are nice. When E is an order invariant constraint, well, we always have E nice. I mean that's part of the invariant maximality, yeah. But where F is nice, the invariance condition has to be order theoretic. We're only talking about order theoretic invariance conditions. In other words, the function F is an order theoretic subset of, now this is wrong, order theoretic subset of uh, two here. That's a two. I didn't. Why doesn't it become a two? Ah, I know why. There we are. Yeah. Remember, our F's are all one variable functions. So the F itself, i.e. the graph, is a two-dimensional set. Yeah. Okay. Now, what do I mean by codes? Well, it's convenient for the code uh, for an order invariant set is just a propositional combination of inequalities. I mean, we had other codes too. We used also, but let's just take the logic approach, the language approach. And now, what is a code for the purpose of this? What is a code for an order theoretic a function? Well, there, parameters are very important. Order theoretic allows parameters. Uh, yeah, I beefed up the section on order equivalence and order invariance. I beefed that section up some, uh, and I haven't put it on the internet yet, but I beefed it up some to include a discussion of order theoretic sets, in addition to order invariant sets. Order theoretic sets are just like order invariant sets, except you're allowed parameters from the space, minus one, one. Okay. So the code for F is just a Boolean a propositional combination of inequalities where you're allowed uh, constants or parameters from the space. Okay, in fact, we show that this is uniform. That is, this is not only pi zero one, but it's provably, there's a pi zero one description which provably works. And the technique is, so I do put some proof ideas here. The technique is worth discussing because it's just Gödel completeness theorem. We associate a theory to this question of whether there's a solution that's invariant, maximal solution that's invariant. We associate a theory, a predicate calculus with equality, um, and the language is less than an S for the prospective solution, uh, constants for the endpoints, constants for the rational number of parameters used for the formula that defines the invariance condition F. And we also have function symbols mapping k tuples to k tuples. which we're not allowed to do in predicate calculus because, but you can split them up and make them, mapping K tuples to one tuples is the only thing that's allowed officially. So you can fix that easily. And the axioms are universe is densely ordered. These constants there are increasing, and we need to respect -1 if one of them is the same as you have to say so. Uh, that S is a solution to the um, that S is a solution to the order constraint has to be formalized like this. All right, as a first order statement, where we're quantifying over K tuples, which is not explicitly legal. Of course, you just split them up, the variables up. Uh, and epsilon E is replaced by uh, the definition of E. All right, and then the maximality. Remember, maximality is maximality with respect to this. It means that if S is false at Y, then if I take Y and these function symbols, G1 through GR -1, uh, that this set is not going to be a subset of E. In other words, the G's conveniently give me a counterexample to uh, that comes from the maximality. In other words, if you have a new Y, then there must be something bad going on. Uh, oh, I guess I forgot to say, I guess I do want to say that the G's go back into S. Where do I want to put that? Yeah. So I do want to say here that I'll just write it for you. The G's map into S only. Yeah, got to say that. Okay. Now you have to also say that S is F invariant. See, these are just function symbols, but here F is already an order theoretic function, which we've already defined. So we say this is obviously the definition of S being F invariant. And we want to formalize f of xi equals y. Maybe this is y. Written using the formula used to define f, right? Where the constants used are the stars of the parameters used in the definition of f. Okay, so notice that this is finally axiomatized and it's purely universal, right? This is finally axiomatized and purely universal. And we want to first prove that if the statement holds, that is, the constraint has an F invariant maximal solution, then I actually get a model of this theory. And that's pretty clear because uh, you can use the maximal constraint S. You use -1, with the usual order. And uh, by the way, when I said it was purely universal, I lied a little bit. I forgot to add the Skolem function for density. Remember, this is supposed to be a dense linear order, so you just have a special binary function that handles that. So I have to add that to it. Anyway, these small points. I have to fix it up, though. All right, so it's obvious that if phi holds, then you can build a model. You'll have the model right in front of your face. The G's are these witnesses are these counterexamples, are these witnesses, and you can make them because you have RCA naught. You can easily define those functions. All right, but then I want to claim that that phi is now just equivalent to con. And that comes from here. The if phi, then I get con. Um, you have to be careful about that, but because this is a universally quantified theory, you can use Herbrand's theorem or code elimination to show that you don't need the inductions. You don't need any induction that isn't already present in WKL naught for the forward direction. And the reverse direction is the very well-known way to do completeness in WKL naught. In fact, you actually get a complete diagram, which is more than you need here. All right, and a corollary is if F is order theoretic and K is greater or equal to 1, the sentences F is usable, F is K usable, F is fully K usable are implicitly pi 0, 1. Because that core piece is pi 0, 1. This just surrounds that core piece, these statements of usability. It's the core thing that you need to check is pi 0, 1. See here. This thing here. You need to check that that's pi 0, 1, which we did, right? Because we proved that it was equivalent to satisfiability, and then we argued that satisfiability is the same as con in this context. All right. So that's it today. Andreas, I'm done today.